Recall that in section 3.2, when we developed our library of functions, we were introduced to the basic parent function for a degree 2 or quadratic function. Recall that it was a basic parabola opening up with its vertex at the origin, and it had the equation y equals x squared. In this section, we're going to take a look at quadratic functions on a more granular level. Just as linear functions can be presented in different forms, the same is true for quadratic functions. We'll first begin in this video by examining vertex form. Now, the good thing about vertex form is that it will allow us to review what we learned about transformations. Here's the definition. The vertex form of a quadratic function is given by f of x equals a times x minus h quantity squared plus k, where ordered pair hk is the vertex of the parabola. So let's pause right there for just a minute. Remember, our parent function is y equals x squared. So what I can see in this vertex form is that we have a horizontal transformation of h units. Remember, when you add or subtract a constant to the argument of the function, it's a horizontal transformation. Because we're subtracting the constant h here, this means that it's going to move our parent function to the right by h units. This is why, even though we have minus h in the equation, the x value of our vertex is positive h. Also notice that we're adding a constant outside the function. When you add a constant or subtract a constant, it causes your function to translate vertically. Adding a constant moves the graph up the y-axis by k units. Since we're translating up by k units, we have a positive k for the y value of our vertex. So just make that observation. I change the sign of the x-coordinate to get the x-coordinate of the vertex, and I keep the same sign for the y-coordinate to get the y-coordinate of the vertex. Now, all of our parabolas are going to be symmetric about a line called an axis of symmetry. X equals h is the equation for the axis of symmetry. As we learned in the previous video, x equal to a constant is the equation of a vertical line. So notice the constant here matches the x-coordinate of our vertex. This simply means that the axis of symmetry is a vertical line passing through the vertex. It's going to divide our parabola in two matching pieces. Now, if this leading coefficient a is positive, then the parabola opens up. If a is negative, that means we have a reflection across the x-axis. It's going to invert the parabola and cause it to open down. So next you see some examples of parabolas. On the first example, notice the parabola opens up. This means its leading coefficient would be positive. Also observe that we have the vertex at 2, -4, and our axis of symmetry passes right through that vertex. This divides our parabola in two matching pieces. In this case, we've got two x-intercepts. So observe the x-intercept to the right of the axis of symmetry is 2 units away, and the x-intercept to the left of that axis of symmetry is also 2 units away. So points on either side of the axis of symmetry are going to be equidistant from that axis of symmetry. So that's an important tool that you can use to make sure that your parabola comes out symmetric. On the next example, one thing's a little bit different about this one, and that is the vertex and the x-intercept are the same point. So this makes our parabola seem to bounce on the x-axis and turn around and go the other way. So on our first example, we had 2 x-intercepts, but on the second one, we have only 1 x-intercept. And if you take a peek at our last example, notice it has 0 x-intercepts. So a parabola can have 2, 1, or 0 x-intercepts. However, all 3 of our parabolas have exactly 1 y-intercept. It's not going to have 2 because then it would cease to be a function, but every parabola has exactly 1 y-intercept. So again, making the observation on the second one, the parabola opens up, so its leading coefficient would be positive, and the parabola in our third example opens down, so its leading coefficient would be negative. So these are the important properties that we want to identify when we graph a parabola. So to graph a parabola, number one, determine the orientation. Does it open up or down? And we can tell that by the sign of the leading coefficient A. Then find the vertex just by reading the transformations from the vertex form of the equation. Once I know the vertex, it's convenient then to write the equation for the axis of symmetry because the x-coordinate of our vertex also shows up in the equation for the axis of symmetry. Also, it's important to remember that the axis of symmetry is a line, so we want to describe the line with an equation. So I don't want to say h is the axis of symmetry. We want to say x equals h. That describes a vertical line. Then we're going to locate the x-intercepts by setting y equal to 0. Remember when we were looking at lines, to find the x-intercept, we set y to 0, and to find the y-intercept, we set x to 0. This is the same plan that we used with lines. It's just applied to a different function. So let's put this all together and try example 1. Graph the quadratic functions by plotting the vertex, axis of symmetry, x and y intercepts. So the first thing I want to do is determine the orientation. Notice the leading coefficient of this parabola is negative. Since that leading coefficient is negative, or a is less than 0, we can anticipate our parabola to open down. Next, we want to determine its vertex. Vertex is easy in vertex form because I can read the transformations. Notice our parabola has been shifted to the right by 2 units, so its original vertex at 0, 0 now lands at x equals positive 2 and y equals 4. Remember, this has gone to the right, this has gone up, so our vertex ordered pair is 2, 4. Once we know the vertex, we can then write the equation for our axis of symmetry. It's always going to be related to the x-coordinate of our vertex. So in this case, the equation for our axis of symmetry is x equals 2. So I'm going to go ahead and update my graph with this information. Our vertex is at ordered pair 2, 4. And our axis of symmetry, which we'll sketch as a vertical dashed line, passes right through that vertex. Its equation is x equals 2. Now, don't forget, we observed that our parabola is going to open down. So if we begin to envision our parabola opening down, notice we can anticipate 2 x-intercepts. So let's find those next. To find the x-intercepts, and we're expecting 2, we're going to set y equal to 0. Now, don't forget, y and f of x are the same thing, so the left side can also be written as y. So I'm going to replace that left side with 0. This is going to lead us to a one-variable quadratic equation. Don't forget, we learned 4 different methods for solving a quadratic equation. The nature of this one points us to the square root method. So I'm going to isolate the squared term by subtracting 4 from both sides. We can divide both sides by -1. Then we can take the square root of both sides. Now don't forget, when we take the square root of both sides, we're going to get 1 positive and 1 negative value. So I'm going to switch the sides of my equation here. On the right side, we have the square root of x minus 2 squared. That gives us x minus 2. The left side, we have plus or minus square root of 4. That gives us plus and minus 2. So adding 2 to both sides and putting it in front of that plus or minus, we have 2 plus or minus 2. So one of our x-intercepts, I'm going to calculate the difference first. 2 minus 2 gives me 0. And don't forget, we set y equal to 0. So one ordered pair, or one x-intercept, is 0, 0. And the other one comes from 2 plus 2. 2 plus 2 is 4. Our y-coordinate is still 0. So we've got 2 x-intercepts. One at 0, 0, which also doubles as the y-intercept, and 4, 0. Now again, since my x-intercept is also on the y-axis, we don't have to do any additional work to find the y-intercept, because remember, every parabola has exactly one y-intercept, and we already found it from the x-intercept. So we can go ahead and sketch our parabola. And do observe that both of my x-intercepts are equidistant from that axis of symmetry. And don't forget, you can certainly check the graph with your calculator and verify your points from the table. Let's practice this again on example B. So let's first observe that the leading coefficient 1/2 is positive. So that leading coefficient, which we call A, is positive. This means our parabola opens up. We can identify the vertex, remembering what we learned about transformations. This parabola has been shifted to the left by 3, so the x-coordinate of our vertex is -3, and it has been shifted down 2 units, so our vertex occurs at -3, -2. Once we have our vertex, we can immediately identify the equation for our axis of symmetry. It is a vertical line, so the form of the line is x equal to a number, and it's always going to be the x-coordinate of our vertex. So on our graph, we have ordered pair -3, -2 for our vertex, and our axis of symmetry passes right through that vertex. And we'll go ahead and label it with its equation, x equals -3. Now remember, we said our parabola is going to open up. So if I began to envision this parabola, it looks like it's going to have 2 x-intercepts. So let's take some time and calculate our x-intercepts. The plan always for calculating an x-intercept, whether it's a linear or quadratic function, is to set y equal to 0. So we need to solve the equation. 0 equals 1/2 times the quantity x plus 3 squared minus 2. So we'll solve this again with the square root method. So our first goal is to isolate that x plus 3 quantity squared. So let's add 2 to both sides. Let's multiply both sides by 2. On the left side, we'd get a 4. On the right side, 2 times 1/2 is 1. So we just end up with x plus 3 quantity squared. Then we're ready to apply our square root method, taking the square root of both sides and remembering plus or minus over here. I'm going to switch it again like I did on the last example and call this x plus 3 equals plus or minus 2. So our x-intercepts will be -3 plus and minus 2. So to show a little more detail, we have -3 minus 2 and -3 plus 2, 2 possible x values. So one of our x values is -5 and the other one is -1. Now that's not an ordered pair. Those are the x values of 2 different ordered pairs. Remember, our corresponding y value here is 0. So our x-intercepts will occur at -5, 0 and -1, 0. So let's plot those on our graph. -5, 0 and -1, 0. And while I'm here, I'm going to check to make sure that they have the same relation to the axis of symmetry on both sides. 2 units away on the left, 2 units away on the right. So it looks like we're in good shape. Now, in this case, because the x-intercept and the y-intercept are not coincident, we need to do the work to find the y-intercept. Remember, anytime you want the y-intercept, no matter what type of function you're dealing with, you're going to set x equal to 0. So I'm going to go back to my original function, and remember, g of x is the same thing as y. So I'm going to write the left side as a y, and I'm going to replace the x with 0. We're going to follow our order of operations. 0 plus 3 is 3, and 3 squared gives us 9. 1/3 of 9 is 3. And 3 minus 2 gives us 1. So putting this together in the correct order, x is 0 and y is 1. So it looks like our y-intercept is 0 and 1. So we can now sketch our graph. It's a little wider because remember, this coefficient 1/2 makes it half as tall than the parent function. So we get something that's a little wider than our first graph. So I'm going to go ahead and label my function, g of x. And once again, you can certainly check all of those points with your calculator.